Imagine waking up inside a steel city moving at 30 knots through open ocean. 5,000 people around you, no land within 500 miles, no external power grid, no municipal water supply, no outside hospital, no fire department, no 911, no internet, no bank, no resupply ship on the horizon. And then imagine that somewhere deep below the waterline, a critical system begins to fail. Not a dramatic explosion, not a visible crisis, just a quiet deviation from a number on a gauge, a pressure dropping where it should hold steady, a temperature rising where it should remain flat. And in the next 60 seconds, the protocols that keep 5,000 human beings alive will either execute exactly as designed or they won't. And there is no third option, because out here, there is no one else coming. That is not a hypothetical. That is Tuesday. That is the operating reality of a nuclear-powered aircraft carrier, and the question that almost no one outside the engineering community ever stops to ask is not how these ships fight, but how they survive, how they maintain order, function, and human stability across months of total self-reliance, and what specific, layered, redundant, pressure-tested emergency protocols stand between 5,000 lives and the kind of cascading failure that civilian infrastructure could never tolerate and never survive. Start with the most fundamental constraint: power. A Nimitz-class, or Gerald R. Ford-class carrier, is driven by two nuclear reactors producing roughly 260 megawatts of thermal energy, enough electricity to power a medium-sized American city. And this is not an engineering flex, it is a survival requirement. Every system aboard, from the catapults that launch aircraft, to the evaporators that convert seawater into drinking water, to the ventilation fans that push breathable air through hundreds of passageways to the refrigeration units holding 90 days of perishable food, every single one of them is downstream of those two reactors. If you lived here, power would not be an abstraction. Power would be the difference between a functioning civilization and a dark, increasingly desperate steel enclosure in open water. And so the emergency protocols around reactor integrity are not merely technical checklists, they are the foundational architecture of order itself. Naval reactors are designed with negative temperature coefficients, meaning that if they begin to overheat, the physics of the reaction naturally suppresses itself, but human protocol layers sit on top of that physics because physics alone is insufficient when you are months from any external support. Watch officers monitor reactor parameters continuously across multi-hour shifts, and the moment any reading deviates beyond its operational band, not dangerously, not catastrophically, just beyond its allowed margin, a response protocol activates that is so deeply rehearsed it functions almost below conscious thought. Drills run constantly, not because catastrophe is imminent, but because the only way to compress response time to a level that prevents cascade is to make the correct action, the automatic action, the one the body performs before the mind has fully registered what is happening. But here's what most people never consider. The reactor emergency protocol is not the hardest protocol to execute. The hardest protocol to execute is the one that runs in parallel to it. The protocol that keeps 5,000 people behaving in an orderly, purposeful, non-panicked way while an invisible technical crisis resolves itself somewhere below them. Human psychology under uncertainty is one of the most dangerous forces aboard a carrier, more unpredictable than any mechanical failure, because mechanical failures follow physics and physics is consistent. But 5,000 people who sense something is wrong and receive no information will generate their own information. And that information will be wrong. And wrong information at scale creates behavior that compounds a technical crisis into a human one. The carrier's command structure understands this with a precision that civilian emergency management rarely achieves. Information flow is controlled not to deceive, but to pace, to release accurate updates at the rate the response team can act on them, so that the crew's understanding of the situation tracks the resolution of the situation rather than racing ahead into speculation. General announcing systems, known as the 1MC, are used with deliberate restraint during system failures for exactly this reason. Silence on the 1MC is a managed variable, not an accident. Now scale the problem. Water. A carrier at sea consumes approximately 400,000 gallons of fresh water per day for drinking, cooking, hygiene, medical sterilization, boiler feed water, and the complex cooling demands of the air wing's machinery. None of that water comes from outside the ship. All of it is produced aboard through evaporation and reverse osmosis systems that strip salt from seawater continuously, and if those systems degrade, the ship does not simply order more water. There is no order to place, there is no supplier, there is a rate of consumption versus a rate of production, and if production falls below consumption, the reserve tanks begin to drop, and the emergency protocol that governs water rationing aboard a carrier is one of the most psychologically taxing to implement because it touches every person in the most intimate and immediate way. Hot showers disappear first, then the duration of showers, then the frequency. Laundry restrictions follow, then dietary simplification. The protocol exists in tiers, each tier pre-approved, pre-communicated, and already known to the crew so that when the announcement comes, and it comes not as a surprise but as the activation of a plan the crew already understands, the response is compliance rather than confusion. That is not a trivial design achievement. That is the product of training culture deliberately engineered to make every sailor an informed participant in the ship's survival logic, rather than a passive occupant of it. This is where civilian logic collapses. In a city ashore, infrastructure failure means calling someone. It means waiting for repair crews who arrive from outside the system. It means the disruption is bounded, uncomfortable, but ultimately external to your own responsibility. Aboard a carrier, every person is inside the system and every person is part of the response. The sailor whose bunk is 12 inches from the next sailor's bunk, who has been awake for 14 hours, who is operating on a sleep schedule determined by the ship's watch rotation rather than natural light. That sailor is expected not merely to tolerate a water restriction but to actively support it, to report overconsumption if they observe it, to adjust their personal routine without being individually managed. The protocol assumes this. It assumes it because it is trained for it, because the culture of the carrier deliberately cultivates a form of collective competence that civilian emergency systems typically have to try to generate from scratch in the middle of a crisis. And this is where the pressure intensifies. Fire. Fire aboard a carrier is not an emergency in the conventional sense. It is an existential scenario with a countdown. Steel conducts heat. Compartments connect through ventilation runs, cable runs, and fluid lines. Jet fuel, ordnance, hydraulic fluid, and electrical insulation all exist in close proximity. And the geography of a carrier means that a fire that is not contained within the first 90 seconds will consume resources, suppression agents, response personnel, breathable air, at a rate that rapidly exceeds the ship's ability to regenerate them. The emergency protocol for fire is therefore not a response protocol. It is a containment protocol, and the distinction is critical. Response suggests reacting to something already underway. Containment means the protocol's primary goal is to shrink the physical and chemical possibility space of the fire before the fire itself understands it has those possibilities. Every compartment aboard a carrier is a fire zone with its own isolation capability, ventilation dampers that close, watertight doors that seal, halon systems that displace oxygen from electrical spaces before a thermal event can develop. The crew trains to activate these boundaries before they know the full scope of what they're containing, because by the time the scope is known, the window for containment may have passed. Damage control parties, distributed across the ship, not centralized, move to their stations not when ordered, but when the alarm sounds, because the protocol has made the alarm itself the order, nay, eliminating the delay of a communication chain in the moments when every second of delay has a consequence. Here's what most people never consider about damage control. The protocol is not designed for the people running toward the fire. It is designed for the 5,000 people who are not. While a damage control party floods a passageway with fire suppression agent, the rest of the crew is executing a parallel protocol, moving away from affected zones via designated routes, clearing passageways for response personnel, accounting for their own work section, so that a missing person can be identified not in the aftermath, but during the event. Accountability is not paperwork in this context. It is a real-time data system that tells the command exactly how many people are unaccounted for and where they were last assigned, compressing a search scenario that could take hours into minutes. If you were here and your name wasn't checked off that list, someone would be looking for you before the fire was out. Medical. A carrier operates a hospital, not a sick bay. A hospital with operating rooms, intensive care capacity, dental surgery, psychiatric care, and pharmacy. Because the nearest alternative is hundreds of miles away, and a medevac flight requires weather, range, and availability that cannot be assumed. The emergency medical protocol aboard a carrier is built around a core constraint that shore-based medicine rarely confronts: finite resupply. Blood products, surgical consumables, anesthetic agents, all of them exist in a quantity that was loaded at the last port call and will not be replenished until the next one. The medical officer tracks consumption against projected need the way an engineer tracks fuel against range, because running short of a critical medication or blood type during a mass casualty event is not a supply chain problem that can be solved with an urgent order. It is a consequence that must be anticipated and prevented by protocol before it becomes acute. Triage standards aboard a carrier are therefore not identical to shore-based triage. They are adjusted for resource reality. Decisions that would be deferred to a specialist consultation ashore are made by the ship's medical team with the information and supplies available to them. And those decisions are supported by telemedicine links to Naval Medical Center Portsmouth and Bethesda. But those links depend on the satellite communication systems that are themselves dependent on power, which returns every thread of this ship's survival logic back to those two reactors humming below the waterline. But this creates a new vulnerability: communication. A carrier's ability to maintain contact with fleet commanders, with medical consultants, with logistics chains, with weather routing services, all of it passes through electromagnetic systems that can be degraded by atmospheric conditions, by electronic warfare environments, by equipment failure, and by the deliberate decision to maintain emissions control when the ship needs to minimize its detectable signature. The Communication Emergency Protocol does not treat blackout as a catastrophe to be avoided. It treats blackout as a condition to be operated within because the ship was designed from its keel upward on the assumption that external communication might not be available, and that every critical function must therefore be executable without it. Medical decisions can be made without telemedicine. Navigation can be maintained without GPS. Engineering can be managed without shore-based technical support. Command authority flows through a succession chain that is drilled so thoroughly that the removal of any individual from the chain, at any level, activates a replacement sequence that is already known to everyone in it. The carrier does not depend on any single person or any single external connection to function. Actually, this is not resilience as an afterthought. This is resilience as the foundational design principle. Now picture the moment when multiple systems begin to fail simultaneously, not sequentially, not cleanly, not in the order that the training scenarios assumed, but in the overlapping, ambiguous, resource-competing way that real emergencies actually unfold. A power fluctuation affects the evaporation plant. The evaporation plant reduction strains the water reserve. The water reserve restriction affects food preparation timing. Food timing affects crew energy and alertness. Crew alertness affects watch quality across every other system. This is the cascade that emergency protocol architecture is specifically designed to interrupt, and it interrupts it not by predicting which systems will fail in which order, but by building enough redundancy, enough trained human response, and enough pre-authorized decision authority at the local level that no single failure point can propagate unchecked before a response is already underway. The officer of the deck does not need to consult a manual to know what to do when water production drops by 15%. The protocol is in the officer's memory, rehearsed to the point where it is no longer a decision, but a reflex, because in the moment when it matters, the time cost of looking something up is a luxury that open ocean does not extend. If resupply didn't arrive, if the scheduled replenishment at sea evolution was canceled by weather, by threat, by operational priority, the carrier would not stop functioning. It would shift into a conservation protocol that had already been calculated, already been communicated, already been accepted by the crew as the operating reality for however long the gap persisted. This is the deepest expression of what a carrier actually is. Not a weapons platform that happens to have living quarters, but a fully engineered, deliberately self-contained human civilization that happens to carry weapons. The distinction matters because it explains why the emergency protocols work. They work not because they are clever or comprehensive, though they are both. They work because every person living inside the system has been trained to understand themselves as part of the system, to see their own behavior as a variable that the system's survival depends on, and to act accordingly even in conditions of stress, fatigue, uncertainty, and physical discomfort that most civilian emergency planning never has to account for as baseline conditions rather than exceptional ones. What remains largely unexplained, even within the public understanding of how carriers operate, is how the ship manages the psychological load of sustained emergency protocol activation across weeks and months rather than hours. A carrier can operate in heightened readiness states for extended periods, and the human cost of that sustained vigilance, the erosion of sleep, the compression of personal space, the accumulation of decisions made under pressure without external validation, these are not solved problems. They are managed problems, addressed through a combination of watch rotation design, mental health integration into the medical protocol, command climate culture, and the small but non-trivial engineering decisions built into the ship's physical spaces that provide moments of acoustic and visual relief in a steel environment that would otherwise be total. How those systems interact with emergency protocol performance over the long arc of a deployment, and what the actual failure threshold of sustained human vigilance looks like before it begins to introduce errors into the very protocols designed to prevent them, is a question that the carrier's designers answered with their best available knowledge, and that every deployment continues to quietly test.